Arkadaşlar, bugünkü Romer Talks serimize hoş geldiniz. Bugünkü misafirimiz Mehmet Efe Tiryaki. Efe ile makine mühendisliği bölümünde öğrencilik döneminden tanışıyoruz ama yıllar benim tahminimden çabuk geçmiş. 2016 yılında bölümümüzden mezun olduktan sonra ETH Zürich'te robotik üzerine master'ını yapıp sonra Max Planck'ta doktorasını tamamladı. Hatta çok taze, dumanı üstünde bir şekilde tamamladı diyebiliriz. Daha bir ayı çıktı mı?
Yok, olmamış.
40'ı çıkmadı daha neredeyse. Oldukça yeni, tebrik ediyoruz tekrar Efe'cim. Hayırlı uğurlu olsun. Bugün Efe bize MRI-powered Magnetic Microrobotics ana başlığı altında çalışmalarını anlatacak. Başlamadan önce tekrar söylemek istediğin şeyler varsa sen de buyur Efe. Onun dışında sunuşu Türkçe, İngilizce nasıl tercih ediyorsan öyle yapabilirsin. Henüz ekran paylaşmadığını da hatırlat.
Daha açmadım. Teşekkür ederim. Ben sunumu İngilizce yapayım. Hani Türkçesi takip edemeyen olursa onu yapar. Benim için biraz zor olur muhtemelen Türkçe yapmak.
Daha da iyi olur. Adı da Romer Talks zaten.
Şöyle verince sanırım gözüküyor şu an.
Şu an şeye geldik. Sunuş ekranına geldik.
Okay. Thank you very much for kind introduction. Today I'm going to talk about work in general on MRI-powered magnetic microrobotics. I hope this will be a different kind of topic for many of our audience. I will talk mainly about different actuation mechanisms, different magnetic robots we have in MRI, and how we try to localize these robot tractors or this kind of applications. So first of all, why we care about MRI in general. Have some. Okay, so a bit, I'm coming one more again. So basically we have all these nice, I know where should I start, but as I say, MRI is one of the most versatile medical imaging modalities in the clinics, and we have many different imaging options like 3D soft tissue imaging, angiographic imaging, blood flow imaging, and even like brain activity imaging options. And we can do all of these in MRI without like exposing the patient to any ionizing radiation. So it's considerably more safe compared to X-ray and CT kind of MRI, CT kind of medical imaging modalities. On top of that, it is a huge electromagnetic system which can apply great amount of magnetic force and torques on the robots, on the magnetic objects. And what we want to achieve is to use this magnetic actuation potential and combine it with medical imaging potential of MRI to create functional medical robots. So what kind of actuation concepts we already have in MRI and how we actuate these robots? In MRI, we have three sets of electromagnetic coil setup, and two of which, main field coil and gradient coils, we could use them to apply magnetic forces and torques on magnetic objects. And in literature, people use these coils to control different kind of robotic systems, such as ferromagnetic beads. Here you see probably hard to see, but there's a 2 millimeter steel sphere that could be steered inside this channel structure using gradient coils of MRI scanners. And we can also put these steel spheres at the tip of a catheter and visualize this catheter and also steer it inside the body. And there are also other actuation methods such as Lorentz force-based actuation, which this work is from Professor Çavuşoğlu's team. They have a coil setup at the tip, and then they can steer catheters also inside MRI scanners. And also we can use the main field of MRI, the large field, to steer magnetic guide wires and catheters. But this time we are not operating inside MRI, but outside of MRI with a large robotic arm that rotates the patient around MRI using MRI such as a large magnetic setup. So after this kind of magnetic actuation potential of MRI, what are the tracking options? Like the main reason we want to use MRI is to track the robot. One really common version is using RF markers, basically some coil setups, small coils that amplify the signals. There's also some more elaborate versions of these with like lots of RL circuits to maximize the signal coming from the marker. The main problem of these markers are that they are geometry dependent, and you cannot really always see them. And in a different problem is that they create lots of they have risk of overheating during MRI imaging, so on. Therefore, there are also passive tracking methods, which uses magnetic materials, which creates dark artifacts in MRI images. By combining imaging and actuation from gradient coils, we can actually create magnetic robots that could be tracked using magnetic artifacts, as you see in this video. We have the artifact coming from the robot, and by applying magnetic gradients, we can move the robot in real time, and we can steer it around. The main problem with this approach, with this 2D MRI imaging with the magnetic particles, is that it takes time. MRI imaging is generally a slow imaging modality, and we need higher speeds to obtain, to achieve closed-loop control of these robots. Therefore, researchers also propose in literature like 1D projection sequences. The main idea is that rather than obtaining 2D full MRI images, they create some sequences generating signal from around the robot only, and then use just 1D projections looking like these plots here to localize the robot. Basically, we can localize the robot simply at the center of these signals. After that, the main problem here is that we have high speed feedback, but we don't have real MRI images, so we don't see the background. What researchers generally does is that they use some other imaging modalities, such as here X-ray images, and then overlay the position of the robot on top of these images. So these are, with the magnetic actuation concepts and the imaging methods, these are the general landscape of MRI-powered magnetic microrobots until now. Now I will talk about, in general, these algorithms and what we worked on that, and then how we developed robotic systems using that. I will mainly focus on 3 different robotic systems in this talk. First one is magnetic capsule robots. The second one is Lorentz force catheters, and lastly, our last work, magnetic guide wires inside MRI. So for the first one, I will mention the gradient actuation-based control for the capsule robots, 1D MRI imaging-based tracking, and 2D MRI imaging-based tracking to cover tracking-based challenges in general in MRI, and then demonstrated. We'll talk about on-demand drug delivery to show some functionalities, potential of these magnetic capsule robots. Later, I will introduce the Lorentz force actuation concepts in MRI, and then talk about some catheter shape tracking approach we were working on, which is still ongoing. And then lastly, I will introduce our new concept, ultra-high-field magnetic actuation, and also show how we can navigate magnetic guide wires using these actuation methods. So starting with the magnetic capsule robots, firstly, what we should consider is that how we actually actuate these capsule robots inside MRI. First of all, let's have a robot, a free spherical robot, magnetic robot. When we introduce that into MRI, what happens that the static field, the 7 Tesla for us, for different MRI scanners, could be 1.5 or 3 Teslas, aligns the robot with the main field. It applies large amount of torques, and then robot aligns its magnetization with the B field. After that, we can apply three-dimensional gradient forces to steer the robot. And to do that, we need to develop our own MRI imaging sequences. Here you have the MRI imaging sequences are the softwares that controls the RF pulses and also gradient pulses inside MRI, and then determine when we are actually getting the signal out of MRI. And in these imaging sequences, we already have our imaging part, and then we need to add our actuation. So the main challenges here is that since we are sharing some of the time with imaging and actuation, we don't really have we don't have the maximum potential of the MRI to steer the robots. In best case, we have half of the time to actuation, and moreover, we have limited gradient forces as a hardware, so we can only go up to like 60 millitesla per meter, which may not mean much for many, but it can move the robots, but it cannot really apply large amount of forces to react to flows, so on, inside the body. And moreover, we also have a duty cycle. The MRI hardware cannot apply all of the forces, the gradients at the same time because of the driver limitations. We generally have a around 20% of the duty cycle of the whole thing. So we are limited by the forces. So we can, if we have a solid sphere, we cannot lift it in MRI. We cannot really move it in three-dimensional space. What we therefore proposed during my PhD was designing capsule robots, which has external polymer shells that encapsulates the magnetic sphere and also air inside the robot to reduce the average density of the robot. Using this system, we were able to show that we can actuate the robots in 3D. Here you see a real kidney image in MRI, and then we have our magnetic robots distortion as this black artifact moving around. Using this capsule robots and magnetic actuation from the MRI, we can actually move our robot in 3D structures of this kidney in the renal cavity, and then move around towards the calyxes of the kidney, which is generally challenging with the tethered tools. So after the actuation, we also go into a bit of control part and ask ourselves what should be the feedback rate to be able to control these robots robustly, MRI imaging and actuation. Therefore, we developed some simulation environments that captures the general forces of MRI and also the fluidic and gravitational forces. With these simulations, we made lots of like randomized control experiments and find out that we need around 10 Hz of feedback rate to be able to control the robots in 3D with reasonable accuracies. Then we go to literature and check what kind of imaging speeds we could have for which kind of robot sizes. We saw that in literature we have 2D and 1D imaging modalities, and only 1D imaging modalities actually can track the robot above 10 Hz. But the problem here is that we don't really have possibility to track the smaller robots in literature. So we look into methods to localize robots with smaller sizes, magnetic materials with smaller sizes. To do that, we need to first understand a bit of MRI imaging. So I will introduce the concepts in general for the projection imaging, especially. In MRI imaging, in slice imaging, MRI slice imaging, we can image certain slice in body by using slice selection gradients and RF pulse frequencies and bandwidths. By selecting those parameters properly, we can create images from certain slice in the body. Using the similar concept, we can also image the magnetic materials inside the patient, inside the MRI. What's changing is that rather than slice selection, we use the magnets on magnetic signature. When we insert our robot inside MRI, it creates a dipole-shaped magnetic field distortion, and therefore the alarm frequency of our the surrounding environment changes. So what we could do, we could change our RF pulses to selectively excite certain regions around our robot. As you can see here, we can basically excite this band and then obtain this band, images from this band. In literature, people tried this approach to track the robots, but they couldn't really achieve tracking below 1 millimeter size scale, where we actually really want to operate. So we repeated some of these experiments with the same parameters in our MRI for different magnetic particles to see if we can scale it down. What we observe is that as we go smaller robot sizes, this approach actually creates so little signals in MRI that the noise, background noise, became really dominant. So we cannot really use it for tracking. After quite a bit of optimization, we find out that actually the optimal excitation pattern for the MRI, like for the RF pulses, is exciting everywhere which is positive, and then create 2D projections such as this image in the right side. So after obtaining this 2D projection, we need to go for the 1D projections. How we actually obtain that? If we get 2D projections in different directions in MRI, we will observe such images in the left. And if we take the Fourier transform in one direction only, we will obtain a stack of 1D projections. Actually, these projections are what MRI collects in the Cartesian imaging. We collect all of them and then obtain the MRI images afterward. And we can already see in these stacks that there is a clear pattern showing the robot position in the vertical axis. Therefore, we don't really need all of them. We just need to select one of them. And in literature, people use the center line of this K-space line to track the robots, which is a problematic choice in general, because center line of a K-space, these projections actually give us some information about the background of the object. I think most of the people here might be familiar with the Fourier transformation of an image. If you have a Fourier transform, the center of the image, K-space, Fourier transform actually show the big objects and the background objects in the image. But we want to track a small object, therefore we propose to use the K-space lines from the peripheral of the K-space and obtain these nice projections, in which we can actually easily spot where is the robot position. But at the end, by just changing RF excitation patterns in MRI and projection selection methods we were able to track the robots to like 500 micrometer diameters, even like 300 micrometer diameters, which like 5 times smaller than the state of art in the literature with the same imaging speeds. After obtaining the projections, all imaging, we go back in our MRI and then show some control. Here we have a real-time feedback control in these channels. We basically obtain the position feedback from the projections here we have, and feed the position information to our controller, which is basically a simple P controller with a density adjustment. And then we can control and steer the robot with sub-millimeter accuracies in these channel structures. After this control, we also check if we can use it in real tissue environment, in ex vivo kidney tissues. The main problem here is that because of the complex signals coming from background, our 1D projections were not really nice anymore. It gets much cloudy, and then tracking accuracies decrease accordingly. Where we had like sub-millimeter accuracies in synthetic environments, in real MRI environment, real tissue environment, we had around like 4 millimeter accuracies, which is like 3 times of the robot's body size. So we need a better way to track these robots than 1D projections. So in the next project, we go to 2D MRI imaging again and investigate with Sinan if we can actually track them better here. So how the magnetic robots look in these 2D images is that if the robot is stationary because of the dipole shaped artifact, we have an ellipsoidal shaped signature. This is nice to track. If we have simple template, we could actually track this shape. But if our robot is moving around, then the shape of this artifact changed significantly. Since we are actually obtaining the signal in K-space rather than in image space, any moving object creates these completely different artifacts. Moreover, if our robot is not inside our MRI image, outside, like slightly outside of the slice, the signal will change, and then we also will not be able to see the robot after a while if we go even further. In literature, people propose simple template-based matching methods to track the robot, and also to improve the tracking in 3D. They also use 3D template stacks, but these approaches in general fails in the tracking of robots while they are moving. What we propose is that using a deep learning-based method, which use a convolutional network that gets 2D MRI images and give us the robot position in X and Y directions in the image, and also the distance of the robot, kind of a depth information using slice images. After training these networks, we were able to actually track the robots using the 2D MRI images. As you can see that we get images for 1 second and then see the trajectory from the previous images. And we can actually track the robot with various shapes. We also test the same idea, our deep learning based tracking method inside real tissue, and we observed that we could actually improve the performance of tracking down to like around millimeters scale errors compared to 1D projections, which was quite a bit of improvement. But to be fair, we were not able to go the same speeds of the imaging with the 2D MRI image, 1D MRI imaging methods. So there's still room to grow in terms of tracking in fast imaging and fast imaging. So after all these actuation methods and also the imaging methods, we also want to show some like functionalities with these robots. That was the main problem in general in our research. We have nice micro robots that moves around, but what we will do with them. So we use the same capsule robot design, but change the design a bit. We introduce a hole on our shell, on our robot's shell, to load some drug inside our robot. Now our robot can actually carry drug, and we want to deliver it to the target regions. To keep the drug inside, we created this simple air bubble based mechanism. When we insert our robot to the water, because of the surface tension around the hole, we capture air bubble, and this air bubble prevent the drug to release. After that, we developed a MRI-compatible robotic focus ultrasound system to release this robot. We have basically here we have a focus ultrasound transducer, which can apply focus pulses, acoustic pulses, to a certain region, and then we have a 2D motorized stage that moves our sample around this focus point. Basically, by applying pulses, we were hoping to achieve drug release. You can see here a simple demo. We apply acoustic pulses to release drug, and then we use MRI-based magnetic actuation to reach new target position, and then we can repeat it many times as we want. At the end, we show that we can actually release the drug locally and move around the intestine and show some nice demos with that. And this was pretty much all for the capsule robot part. Now I will talk about the Lorentz force-based catheters. The rest of the presentation is about more of not wireless robot, but tethered robots. First, I will talk this part. That we developed with our colleague Martin in our lab. What happens if we have a loop inside MRI? If we have a simple coil loop, like a copper wire, and then we pass current, we actually apply quite a bit of magnetic torques on this copper wire loop we have. I think many of you might be familiar with this concept, Lorentz force, from like first year physics. If you have a large amount of B field, you can apply a large amount of magnetic forces. And luckily in our MRI, we have like a 7 Tesla B field, so we can actually apply quite a bit of forces. So to use this system, our colleague created these nice coil setups, some saddle coils that we wrap around our catheter actually. And we also have some axial coils on this tip of the catheter. And by applying currents, we can actually steer them. Here in this video, you see a camera view in MRI, where we are actually steering this, okay, play it again. We can steer this catheter in these targets and reach to certain target locations. And we also have the same setup inside with MR imaging. We can actually steer the catheter using MR image feedback. In this case, it's an open loop feedback, and steer through different target locations and reach, perform some, hopefully perform some medical operations in future. So to give some background, since we have all robotics people, maybe I want to talk about a bit how we control these robots. Previous ones were actually like the open loop controller. Here we have a simple, not really simple, but like a cross-rod rod model-based control scheme. We discretize our robot's body to multiple points, and then we build a nonlinear ordinary differential equation set to model our robot, and to decide the required actuation we need for steering the robot. We use an optimization-based torque calculation. Here we have a simple like desired orientation task, and then we have our dynamics coming from the cost model. We optimize it to calculate the required tip torque for desired navigation task. And since we have multiple coils in our setup, we also have a simple current distribution approach. So we have kind of a redundancy. If we don't optimize the currents, we can actually burn our coil by applying too much current. Using this model, we made some simple experiments and show that we can actually reach some different angle targets. And because of our optimal current distribution task, we can actually achieve a large amount of curvatures without really burning our catheter, which is a major challenge and risk in all MRI-based robotic systems. And after all of these modeling and actuation, we also want to show a bit of get into shape sensing and controlling the robot tip position in a closed manner. What we do here is that we basically add some simple magnets at the tip of our catheter and try to use our 1D projections. And then we build again a simple optimization-based curvature estimation, where we try to minimize this time the tip position in our model and the difference between the position in our model and the position feedback we obtain from MRI projections. Using that, we can actually measure the curvature of our robot and then predict position to create a control feedback. We demonstrated a bit control here again. We build a simple control loop using inverse kinematic calculation with COSRAD model, and also add some like compensation with a simple P controller to control the tip position and also the insertion of the catheter. You can see here that we have like RVS visualizations of the catheter. We are giving some different target locations, and our catheter is trying to track it. I'm sorry for this video. It's really dark because we cannot really put lights inside MRI, but we have a camera view here showing the position of the robot also while we are moving. The main problem with this current tracking and closed-loop control of the Lorentz force catheter is that it is an electromagnetic setup, and it also interact with the MRI images quite a bit because of RF interactions. So we also nowadays we are looking different ways to track the robots. One way we did was actually stop using Lorentz force and then looking for magnetically actuated catheters, which will be the last section of the talk. In this part, I will talk about the magnetic guide wires we have. It's a relatively new concept. We published it, I think, around 2 months ago or something. So what we want is actually use MRIs, all this magnetic actuation also for the steering the guide wires. In literature, as I say, we have a couple of different options. People demonstrated like using gradient actuation to steer the robots, but since we don't have much forces with the gradient actuation, they need large magnetic spheres, and the catheter size they can control is relatively large for many operations. And there's a second option is using the outside magnetic field, the main field, to steer the robot. But with this case, because of the large amount of magnetic torques, they were able to control even smaller magnetic materials, magnetic guide wires, but they required a large robotic arm, which to me is not a smart idea in a hospital to put an industrial arm in an MRI lab. So we look for different options. We say that there should be a simpler way, and therefore we find out this whole ultra-magnetic field actuation concept, which was not really studied in literature at all, so was quite exciting for us. So to understand what's happening with the ultra-high field magnetic actuation, I need to talk about a bit magnetization concepts, or maybe this will be quite new for many listeners in the Zoom talk. So what happens if we have a magnet inside a like when we are actuating with magnetic field? Let's say we have our magnet with this theta angle, and we have this hysteresis loop describing the magnetization and the magnetic field, extramagnetic field. If we apply small magnetic fields to our robot, we are actually operating really close to the remnants of our magnetic material. So we don't really change the magnetization of the robot a lot. So we can, in many applications, we assume that we have constant magnetization and we have low fields in many robotics application in magnetic robotics. If we increase the magnetic field a bit more, then what we observe is that the magnetization will start changing significantly towards the direction of the magnetic field we are applying. And if we apply even further, we will reach a saturation magnetization that we cannot really increase the amount of the absolute value of magnetic forces, magnetization vector. If we increase beyond this magnetic field, extramagnetic field, then we will now be in what we call ultra-high field region, where our magnetization doesn't change, but it rotates towards the magnetic, the external magnetic field direction. To be able to calculate the magnetic forces and torques acting on our magnet, now we need to know what is this magnetization angle, theta, phi, my bad. Phi. We are calculating that using some, again, optimization methods, energy optimization, magnetic energy optimization, where we have some potential energy coming from crystal anisotropy energy of our magnet, and also some magnetic energy coming from our external magnetic field. We can consider this like a spring that controls the direction of like an angular spin controls direction of the magnetization, and we can control it with applying more and less magnetic field. So after understanding all this, the magnetization angle, we can calculate the torques we need to actuate the robot if we know the magnetic field and the magnetic field gradients acting on our magnet. Understanding this whole magnetization and torques and forces, we developed some nice simple guide wires with my intern Yiğit last summer. We basically have one magnet at the tip of the guide wire, and we propose 3 different orientations, configurations, depending on the magnet orientation. After that, we again go back and made some modeling effort. We created a Cosrat road model-based real-time simulation environment that can visualize what's happening to our guide wire during we are operating inside MRI. And using this simulation environment, we model our guide wire. Here we need to select the guide wire stiffness and the core diameter, and to be able to use our MRI for actuation in a maximum manner, we first need to maximize the bendings, the amount of bending at ultra-high fields. For us, it's 7 Tesla. And we also need to maximize the range of motion of this catheter, like so how much we are actually if we move from 0.5 Tesla to 7 Tesla. After optimizing our stiffness parameters for these two, we selected some nominal parameters and then build our guide wire. And then we go back in our MRI to build a robotic stage to actually actuate this. First thing we did is we built a robotic MRI stage which has a camera for top view tracking the robot in MRI. And we also have a motorized stage which can rotate the stage in this theta angle, and also move this whole stage inside of MRI and outside MRI from 0.5 Tesla to 7 Tesla to control the magnetics of the MRI scanner, the magnetic field we are applying our guide wire. So with this setup, we tested our guide wires. We first started with the parallel one, which was also used in literature previously with this robotic arm study. We could actually steer the robot to different targets by using the magnetic torque and then rotating the stage. That actually effectively does bring us where we want to go, but the problem is that we need to rotate the stage, and this is not a smart idea again in MRI, because like it's a really limited area and we cannot really rotate a patient inside MRI. Therefore, we start looking into perpendicular magnetic magnets, the guide wire perpendicular magnet. Here we can also use the magnetic like high field rotations and also different kind of actuation. But the nice thing here is that we have a base twist option. We can basically twist the catheter or guide wire outside of MRI and steer the robot using this approach, and we can reach different directions with these guide wires. And lastly, we can also use anti-parallel configuration, where the benefit of anti-parallel configuration is that now we have a large amount of magnetic torques that rotates more than 90 degrees, and we can also use the base twist actuation like the perpendicular one. And one bonus way of actuation is actually switching the magnetization direction. If we move in MRI while we are physically constrained, we switch the magnetization direction to parallel, and then with this one we can actually go further inside our navigation task and reach different locations. So after checking this basic actuation mechanisms, we go in to demonstrate some navigation potential of these guide wires. We build some glass models of different arteries. For instance, here we have a renal artery. Using anti-parallel guide wire with large amount of rotations, we can actually navigate our guide wire inside renal arteries, and by controlling the amount of magnetic field we apply on our guide wire, as you see here, 2 Tesla, for instance, we can steer to different branches as well. We also showed navigation in more like constrained branch-like structures. Here we have a model of the common curved artery. By using base twist and simple magnetic torquing, we can actually target different branches with this guide wire. And until now, we only do like camera imaging, but we are using MRI, so we also want to use MRI imaging to track what's happening. But the main challenge here is that since we need to operate our robot at the center of MRI, we have a constant field. We cannot go in and out to apply forces. So we changed the design a bit and we introduced a stiff catheter on top of our guide wire, which actually help us to change the free length of the guide wire. If we move the catheter all the way to end, we will have a stiff guide wire that we cannot rotate much. And if we pull it back, we could actually move a lot. And in this MRI image, real-time images, you see our magnet at the tip. With the 0 free length, we can go directly to forward. And if we change the free length, we can actually steer to different locations in the kidney and reach where we can reach directions that we cannot really reach with traditional tools with our guide wire. So that was pretty much all I have for the projects. As a overall contributions and summary in our work, I want to show with the guide wire, with the CAPS robots, we show lots of MRI-powered gradient actuation and show the potential, and demonstrated some new MRI-based tracking methods. And I think we are the first time in literature showing autonomous navigation with these kind of capsule robots, and also some like functionalities with by using this drug delivery approach. And for the Lorentz actuation and actuation and actuated catheters, sorry, my bad. We show some like closed control and some nice energy, like heat mitigating actuation strategies. And lastly, this whole ultra high field actuation concept is a new field in magnetic robotics to me. I mean, we are kind of now leading that. Hopefully in a couple of years, there will be much more new exciting studies, and we already demonstrated like quite a bit of guide wire steering. I believe in like there's still quite a bit of future in the MRI based magnetic actuation. We are actually nearly started the whole thing. There are a couple of like really nice studies in literature, but it's an exciting point to hope in if like anyone interested. In future, we need like for the capsule robots, we need many more studies for faster 2D MRI imaging, and if anyone interested in. And also we need different methods to use MRI to track robots. Currently, we are in our lab working on new NMR-based magnetometer setups to track the robots using magnetic signature. And also, we always need to work on much more complicated and useful medical functionalities with these capsule robots, and try to see if they can be used in clinics. And for the tethered tools, we already have nice actuation concepts, but we need more dexterous actuations with ultra high field and also with the Lorentz force. We are now working on combining these two approaches and create some different kind of guide wires and catheters to steer around in MRI. And we also in parallel, I think this summer we will start working on like MRI-based shape sensing and tracking these guide wires for closed loop control to create autonomous structures. I think this is the direction of the field in general for like people try to generate closed loop controlled autonomous catheter systems for medical interventions. And here we the link actually here the item for that. Now we will move towards more on the closed loop control and autonomy and see if we can use MRI for more like interventional operations. And that's pretty much all of my talk. I hope I didn't bore you. And if you have any questions, please feel free to ask. These are all of my collaborators and my team in Max Planck, our team.